being able to name or classify individual compounds is something common in all our history. I mean, you can even reference Shakespeare in Romeo and Juliet. And even in that case, they were hoping that they could kind of ignore their names. Well, unfortunately, depending on your perspective, we can't ignore names in organic chemistry. So we have to come up with some way to name our compounds consistently so that we are always aware of exactly what name to call something and there is no ambiguity. That said, there are multiple ways to go through and name things, but you have to really only answer to one naming system, and that becomes tricky. So what we'll go through and do is walk through some rules on doing assigning names and try to set it up so that it is straightforward as possible, that you will always consistently get to the same correct answer. So one of our big things, if we address the bottom line there, is that we're trying to identify molecules that are not the same when placed under normal conditions. And we'll address what both those things are really referencing. It's kind of a difficult concept to deal with, and that's why we have nomenclature. Within this video, I want to address that you are aware of this pause to work thing. So that will pop up every so often. What I would recommend you do at that point in the video is pause the video and do whatever work the slide is requesting you to go through and do. If you don't pause it, you'll immediately hear me talk through an explanation on it. So ideally, if you see it, you should click pause, solve it on your own, and then check your work with what I end up working through. So it should disappear. Here's our big, massive slide that has all of our rules when it comes to nomenclature. Some kind of key characteristics that you're going to need to nail down or need to commit to memory, if not everything on here, is the number of carbons. So we're looking at organic chemistry, we have to come up with a shorthand to reference the number of carbons in our structure. So you need to be aware of those abbreviations. So 1 carbon is meth, 2 carbons eth, and so forth. The next part is we will see a variety of different functional groups throughout this semester and next. So we need to be able to name those functional groups. And depending on their level of importance, we may need to name one functional group over the other in kind of a sequence. So there is an organized priority of naming when looking at our functional groups. This is the priority that you're going to have to watch out for. I will point out right out of the gate that we do have this odd situation happening with our alkenes and alkynes. And when we talk about them, we'll see why that's labeled as 7 and 7b. When it comes to assigning which functional group name, I tried to provide within this table 2 bits of information. So number 1, if that is the highest priority functional group, an alkyne, then that is going to be the suffix of your name, okay, for that compound. If there is a higher priority group, then the name instead, for instance, if we had an alkyne and, let's say, a ketone, so if we had both of these functional groups present, the alkyne name would change to this YNE ending. Okay? You notice the dashes are supposed to imply that we've got the rest of the name extending off either direction. So we would show that YNE, and we would instead end the name with the -one, which was our ketone ending name, because the ketone is a higher priority than the alkyne. Next little small box that we see showing up in the wherever it is if we have ring structures, we'll refer to them as cyclocompounds, because bicycle, cycle, cyclic. And when we refer to them as cyclo, we need to be a little bit more careful about establishing their main chain. So if our structure carbons is less than the number of ring carbons, then our ring carbons will be the main chain. And we'll talk about what main chain means. If instead the number of ring carbons is less than the number of structure carbons, then the structure carbons will get named as the main chain. Okay, and it's an important distinction to make there, so just kind of be aware of that as we pass through these. The very last box is kind of how we put this all together. So we'll start out with our very first rule. We need to find our longest carbon chain. It needs to contain the highest priority functional group. We'll then identify the highest priority functional group and any substituent, so anything that is not directly identified within the longest carbon chain. We will then define the location for each and every single one of the items outlined in step 2. We will use the smallest number possible to define that location. Okay? And if we run into a tie situation where we could number from any direction and we end up with the same numbers, we'll use the smallest overall numbers possible. Okay? Last thing we do is put the name all together, okay? Typically in alphabetical order. There are some extra symbols that can show up in there. Those symbols are being referenced in kind of the bolded, which isn't super obvious, but in that first case we can use a dash whenever we have a number followed by a letter. Okay? We'll use that dash. If we have two numbers, we have to include a comma. The comma is there to make sure that we aren't realizing we've got a much larger number. The next part is these parentheses. If for some reason we have a really complex substituent, we need to make sure that that name for the substituent doesn't affect the overall structure. It doesn't get confused with the rest of the structure. So we'll put parentheses around it to kind of separate it out. And then it's just a general rule of thumb, avoid spaces in your name. There are a few cases where spaces are important, but in most cases there will not be a space in your name. For anybody that's using this outside of the context of my class, online homework systems notorious for being very nasty nitpicky for these kind of symbols, including the spaces, so watch out for that. So, let's get right into it. Identifying the main chain. So what we want to do is find the longest carbon chain that includes the highest priority functional group. So we've got a variety of examples up here in different formats. So if we start with the first upper left corner, we've got 1, 2, 3, 4 carbons. So we could say that that is our main chain. Okay? If we move to the next example, we have 1, 2, 3, 4 carbons. So we could identify that as our main chain. And you'll notice in each of these cases what I'm doing is circling them. We move to the next example, same deal. We're identifying the main chain. Okay? So in those first 3 examples, you may notice that we had 4 carbons in each and every single one of them, in the exact same number of hydrogens. And yet, if we went through to name these, we would end up with the exact same name. But are they all the same structure? If I tried to take, say, the structure on the left and overlay it on the structure in the middle, would it overlay? Well, no, they wouldn't, because I've got this bond is aimed downwards as opposed to the upwards in the other case. So now this comes back to dealing with our nomenclature. Remember, we define them as being not the same. Well, these aren't the same with the individual orientation under normal conditions. Well, what's our normal conditions? This has to do with ultimately temperature. How much energy is provided in a general system? In this case, we have enough energy at room temperature to allow for the sigma bond to freely rotate. Well, if that sigma bond freely rotates, these structures are the same, which then means they would get the exact same name. So we have to watch out for that because that can affect our naming system and ultimately identifying our longest carbon chain. So if I remember correctly, what I would like you to go through and do now is take a look at these bottom structures and identify the main chain. There's our pause to work sign. So go through and do that, and now we'll go through and identify those longest chains. So if we go through, and this is the standard format that we would do for a student, 1, 2, 3, 4, 5, 6, 7. You say, okay, well, it's 7 carbons because it's all in that straight line. We have to realize that we are not allowed to, or that our structure can have sigma bond rotation, which means when we draw it, we aren't necessarily drawing it where our longest carbon chain is on that axis. If I go through and now count here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So in the red dots, I highlighted the wrong main chain. So in this case, I want to go through and highlight this as my main chain. And again, you'll notice I'm maintaining this pattern of circling the main chain, which is an important step when trying to go through and identify this. On the other structure, you'll notice that we actually have a ring, right? And some kind of carbons hanging off the side. So again, we want to go through and approach how we identify the main chain. Okay, our longest carbon chain, a typical student might go through and say, well, this is now my longest carbon chain. Well, this is a bit weird, because when you go through and count this, you seem to accept that, but then realize there's another carbon right there. So as soon as I hit this cyclic structure, I now end up counting carbons forever, okay, which is why the cyclic structures have a different nomenclature system. So what we would go through and do is count the carbons in our ring, which in this case would be 5, and we would count the carbons in the longest continuous chain in our substituent. Okay, notice that I am not highlighting that last carbon because it's not part of the same length of chain. It is a branch coming off of it. So now what I would do is go back to that ring rule that we had and decide how many carbons or which part had the most amount of carbons. In this case, my ring has the most carbons. That is now my main chain for that structure. It's not the exterior carbons. Okay? So we've now gone through and identified our longest chain. Okay? So things to watch out for. Sigma bond rotations. A quick sigma bond rotation can make a carbon chain longer or shorter in your view of it. It doesn't change how we name it. Okay? It must be the longest carbon chain, period. Okay? The other thing we've got to watch out for is that rings make their own chain. Okay? And that was what we defined here. That ring is making its own chain of 5 carbons. If for some reason we had changed this structure and I'd added, say, 2 carbons out here, well, now what happens? Well, I would have had 5 carbons in my ring structure, and I would have had 1, 2, 3, 4, 5 carbons in the external structure. So we have a tie situation here. We can decide to go either way. We can name either the blue or the red as our main chain. Let's be a little bit less ambiguous. Let's add 1 more carbon out there. I would now have 6 carbons outside the ring. The 6 carbon structure becomes the main chain. You'll notice that when highlighting that main chain, I do not highlight the atom of the ring that's connected to the main chain. Okay, that is not part of my chain, it's connected to it. Okay? So, what do we do now? Well, we move on to step 2, and what we would want to identify is label our substituents. And our substituents will get marked with a YL for simple carbon substituents. So, we'd go back to our structure. We want to identify our longest carbon chain. Okay, and unfortunately we don't have that still circled, but we can go through and highlight that now. There's our longest carbon chain. For our ring, we had this one. Okay. For that next one, we got a new little structure here that's floating into this. Whoops. And we've got this as our longest carbon chain. Okay, that next one was a little bit trickier. So I'm going to press the pause for a moment here before we explain that. Okay, so why did I highlight that particular carbon chain? Okay. Well, I have to include the longest carbon chain that includes my highest priority functional group. This group out here happens to be a carboxylic acid, which is the highest priority functional group when it comes to naming. How does that affect our name? Well, we'll name it as an oic acid. How do we know that? That was part of the naming system on that very first slide. We look at our other substituents. We have an NH2. The NH2 is named as an amine if it is the highest priority functional group. Well, it's not the highest priority functional group, so it gets named instead as an amino. And the name would continue to the right. If we continue to look at our substituents, up here I have a methyl. Okay? And that's the rest of the substituents. The hydrogen, you'll notice in our list, was never ever specified because it's always kind of backfilling. There is one extra functional group that is a bit odd. Okay? It is within the main chain. That is actually our alkene. Okay? And our alkene had a special nomenclature system. If it wasn't the main one, it goes ene like so. Okay? If we use that same kind of reasoning on our other structures, what we'll end up with will be, if I real quickly draw this out, we've got a methyl up here, we've got an ethyl here, we have another ethyl here. If we go through and look at our other structure, this one's actually going to be an interesting one to go through and name. We have a 1, 2, 3 carbon structure, which would be a propyl, but this is a bit bizarre because within that structure of my longest carbon chain, I have a substituent. Okay, so we'll get through on putting that together. From our previous slide, what we should have picked up also was the name for our main chain. 1, 2, 3, 4, 5, 6, 7, 8, 9 structures. This would be a nonane for 9 carbons. Our next one over is a cyclo, because it's a ring, pentane. Okay. And then our last one down at the bottom had 1, 2, 3, 4, 5 carbons. So we're looking at a pentane. But if we write that AN, we're now saying it's all single bonds. It's just an alkane. Well, it's not just an alkane. It had an alkene within it. So it's going to have to become a pentene. Okay? And since we don't know the ending yet, because there's another higher priority functional group, we'll have to kind of separate that out. So we're slowly kind of layering our information down within each of our work to try and process and eventually get to the point of putting everything together. Okay? So, now with all that extra information, we're going to pause. I'm going to pause the video real quickly. And continuing on, this is actually when that little pause sign should show up. And if I had it show up, it would delete all my work. So we're not going to have it show up. So take a moment, pause, and answer this number 3 question. We now need to define the location of each substituent. So we'll number our chain in such a way that the highest priority group gets the lowest number. Okay, we'll also start to group like substituents with a Greek prefix. So if we start with our upper left structure, I need to now start specifying the location for each of these. So it's now going to be deciding, how do I number? Do I number from right to left, in which case it would be 1, 2, 3, 4, 5, 6, 7, 8, 9, or do I number left to right? 1, 2, 3, 4. And I'm actually going to stop right at that 4 because that's all I really need to answer this. If I number it left to right, my first substituent shows up at position 4. If I number it right to left, my first substituent shows up at number 3. The goal in this is to put the lowest numbers in here, which means I'm going to number right to left. So we'll delete those. that means the methyl shows up at position 3. The ethyl, or one of our ethyls, shows up at position 4. The other ethyl shows up at position 6. We've also made the statement that we need to group like substituents. So since these ethyls are the same, I'm going to group them. And I will now number this 4, 6, so there's my comma, and now my dash, diethyl as my substituent name. So I've simplified that down a little bit. And that can make life a little bit easier when we come through with lots of groups. Notice the diethyl is to reference that there are 2 ethyl groups, so I need to specify the Greek prefix for how many there are. If we go through and move to our cyclopentane structure, okay, where is the propyl group on the cyclopentane? Well, this one, the cyclopentane, where do I start numbering? I can pick any location I want. Okay, but again, I want the lowest possible numbers first for my substituents, which means the first substituent is going to show up at position 1 by definition. So I can go through and now label that substituent will show up at the 1 position. We actually had a substituent within a substituent. Remember that methyl group was a part of that propyl. Okay, well, where did that methyl group show up within the propyl? Well, that means I have to be able to number the propyl. Your substituents will by definition start at position 1 where they are connected to the main chain. So if I go through and number my propyl, I'm at 1, 2, 3, like so. This means that the methyl showed up at position 2. Here's where we have to come in with those parentheses. If I now start to organize and bring the substituent down, how would I name it? Well, at position 1 on the cyclopentane, I have a propyl that has a 2-methyl on it. So I would then need to say 2-methyl propyl to condense that substituent. But that then becomes a problem. I have a 1 and a 2. Well, anywhere I had numbers, I could write a comma. But then it starts to look like I'm saying at position 1 and 2 on the ring. Okay, so this is where our parentheses come in handy. This is at the 1 position, I have the substituent 2-methyl propyl. Okay, so we're putting a name inside of a name, and this could get really tedious because it could be a name inside of a name inside of a name. That's how we would at least name this substituent. If we go to our final structure, where do we locate everything? Well, since the the carboxylic acid is our highest priority functional group, it by definition is going to be position 1. Everything else is then going to follow off of that, which means our acid starts at 1. The amino will be at position 2. The methyl is at position 3. And before we forget it, the alkene is at position 3 as well. You might say, well, isn't it at, didn't number that correctly, isn't it at position 3 and 4? Well, yes, but when we go through to name it, we're only going to name where it first appears, because naturally our double bond is going to continue through to the next carbon. Okay, so it has to be part of that chain, which means we'll only reference it as the 3-alkene. But this again addresses another issue. How do I bring that 3 into the name? Because remember, we've already started to condense our name here. It's a pentene. Okay, so that comes in by saying pent-3-ene. That's how I would kind of start to fold that name into it. Okay, so now that we've got the locations for each of our substituents labeled, I'm going to end up going through and deleting all of my lovely work again as we move into our next step. There's our stupid pause sign again. Putting the name together. So we now need to combine all of these individual pieces and assemble in the alphabetical order to get the final name for the compound. So again, we're going to hit this pause to work, go through and spend some time to do it on your own, and now we'll go through and solve it all together again. And again, with all of our pieces now put out here, we want to assemble them. So if we start with our nonane structure, we now want to put that 3-methyl and that 4,6-diethyl up with it. We want to assemble according to alphabet. Believe it or not, when we look at our alphabet, E comes before M. And you'll notice that I actually did not reference the di in that alphabetization. Okay? The di we will ignore, we go off of the main piece of our substituent. Which then means when I go through to put the final name together, I will end up with 4, 6, hopefully this will all fit in here, diethyl dash 3 dash methyl nonane. That is now the final name for this structure, all put together in one big giant piece. If we go through and look at the next structure, I now need to combine the one substituent with the one name, which is nice because it all fits together as one big thing. Except trying to space this out right is going to be difficult. Let's see if I can do it. 2-methyl propyl, that wasn't too bad. The one out front. And I now have the full name for that structure. Okay, putting all the pieces together. If we go through to the last one, which is by far the most complex, okay, the first thing that I would add in there would actually be the ending. Since the ic acid, or our carboxylic acid, is the highest priority functional group, it goes in at the end. I would end up with 1 oic acid at the end of my name. Okay. The next part of this is I'm going to run out of space very quickly to squeeze in the rest of it. We got to decide between the methyl and the amino, which should come first. Well, alphabetical order, the amino needs to come first in the name, which then means the 3-methyl is what leads up into the pentyl, or the pent. HTEM, oh my gosh, 3. There'd be a dash in front of that 3, and then in front of that we would have the 2 amino dash 3 dash methyl pent 3-ene 1 oic acid. All of these individual pieces need to come together to build the name. Okay, so let's simplify this down and just look at those names for a second. What we are trying to do is come up with something that is universally applicable to all structures that can come out of there. That bottommost structure is probably the most advanced one, and not one you're super responsible for, at least yet. Okay, that's kind of our end game. The first two, you are responsible for knowing how to put together and process, though the same rules apply even when we move to the bottom one. Okay? It's just a slightly more complex version with functional groups that we haven't technically talked about. Okay? So, is there anything we can do to simplify the names? Well, for that first one, no. That is the end of that name. Within it, there should be no spaces. We should be running that all together in a nice, beautiful, long line. We could now come up with the name of this, or the structure from this name, by processing it out. To process it, okay, if we were given the name first, I would generally recommend that what you should start with would be the end of the name, nonane. So we've got 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9. The ane, as the next part, means they're all singly bound. I have a methyl at 3 position, so 1, 2, 3. There's my methyl. At the 4, I have an ethyl. At the 5, 6, I have an ethyl as well. Notice that my structural drawing looks different than the original provided. Completely irrelevant. Okay? We can do any single bond rotations we want as long as we end up with the same structure, and in this case, indeed we do. If we move over to that ring structure, we do have a simplification on this one. Since by definition, carbon number 1 is right here, our substituent will always be at number 1, I can erase the leading 1. Where this then becomes dicey is then could I erase the parentheses? Believe it or not, yes. Why does that then cause problems? Well, because then when we go through to look at, if I can spell right, no, it's just a C. If we then go through to process the name, it says 2-methylpropyl cyclopentane. Okay, well, we have methylpropyl both tied to a 2, okay, and that's not allowed. Every time we have a substituent, we have to specify the number. So because that is a weird thing to do in this case, really what's happened is that we would have to recognize that there are implied parentheses here. It is nasty, I know, it happens every so often, watch out for it. In the last case, could we go through and simplify and alter this name around? Well, for the same reason that we could remove the 1 off of our cyclopentane structure, we can remove the 1 out of our enoic acid. Okay? And by removing it, we would then also remove all of the space there as well and condense that down into one word. Almost one word. There is a space between the ic and the acid, so we do have a space there. Okay? And then this is a perfectly valid name. Okay? And we would hope that there wouldn't be any other way we could have written it. Unfortunately, there is. If we go through for a minute and actually write that out, 2-amino, 3-methyl, we could run into 3-pentene, oic, that looks like a space, that's not a space, there's a space, acid. Why am I allowed to drop that 3 out in front of the pentene? Okay, well, this has to do with what it's referencing. The only thing that that 3 could reference would be a functional group that follows it. Okay, well, we have two options. We either have the ene or the oic acid. Well, since by definition the acid has to have the lowest number and it shows up at the end of a chain, it will always be 1. That means I can slide the 3 out front. That 3 will then naturally apply only to the ene portion of the name, the alkene. Okay, a bit dodgy, but it is there. Okay? At this point, you have the basic rules to be able to go through and apply things or apply your nomenclature. Now it's just a question of practice, practice, practice.